is that, well, not, I see these, there are three things I want to say. First one, just to give you an idea, if you had a layer made out of a very low permeability material, like a mud rock with 100 nanodarcy permeability, and it's 100 meters thick, which is 300 feet, it would take about 3,000 years for the pore pressure to dissipate. That's when we're saying that it takes a long time for water to get out of tiny pore spaces. Well, in this case, in shale, it would take about 3,000 years for that pressure to equilibrate. If you do not have that time, you're going to have overpressure. In a sand, on the contrary, if you have a large permeability, like 100 millidarcy, it would just take a day. So you wouldn't expect this type of overpressure in the sand, but you would do it in a mud rock. Second thing, another very common cause of overpressure that I didn't mention in my notes, but you can see it over here. It's basically when you have a column of fluid with a different density. For example, let's say that we have a reservoir which is filled with gas because of buoyancy, it goes up, and as you go through this part of the rock, the density of the gas is going to be different. So the hydrostatic column inside the gas reservoir is going to be different to the hydrostatic pressure outside. And because of that, if this is the hydrostatic water trend and this is the hydrostatic trend inside the gas layer, you're going to have a difference here that has to be taken by the cap rock. What happens when you're drilling and you hit a spot of very high pressure? What do you get? You get a kick, right? And this is one of the reasons of the kick, because especially when you get to an accumulation of hydrocarbons with a large column of gas or a low density hydrocarbon, then because of the differences in hydrostatic pressure, you will get a large pressure there at the top. And I said there was a third thing I wanted to say related to overpressure, and it is the opposite case to overpressure. Probably you saw the answer over there. When sometimes we said we can have pore pressure which is higher than hydrostatic. Some other times we can have pressure lower than hydrostatic. What could be the reason for that? Any guess? This is a problem, especially now in the Permian Basin.
So
Is the well deflated?
If the reservoirs are depleted, right? If you produce formations for a long time and you don't give enough time to re-equilibrate with the natural pressure and any water dry mechanisms that there may be there, the pressure is going to stay low. And we're going to see later on that it's very important, because when you go through reservoir depletion, you could have regions in which the pore pressure is much lower than hydrostatic. So the line of pore pressure, as you get to a depleted formation, it gets lower. And because of that, you also have a very sharp decrease of the fracture gradient. So if you were to drill, for example, at a given mud weight, and you get to a very low region with a low fracture gradient, as soon as you hit that point, you're going to create a hydraulic fracture, and you're going to have mud losses in that region because your fracture gradient is too low and your pressure is enough to cause a hydraulic fracture, and course, that's not good, right? So I was bringing the case of the Victoria Basin because we have over there many very depleted formations, and now when we need to go deeper into the source rock, we have to go through those, and you have to avoid drilling problems when you go through those depleted formations. Okay, so I think we are done with overpressure, and now we're going to talk about one other very important topic, which are horizontal stresses. Oh, I just forgot one more thing. Last thing about overpressure. There is one more cause of overpressure, which is very important. It's also related to shales, which is hydrocarbon generation. When hydrocarbons start to cook inside the source rock, there is a change of fluid volume so that the hydrocarbons occupy a larger volume than the initial components, so you have overpressure generated in the source rock. Actually, for shales, for example, that's good. Having overpressure, that's good because it tells you that there are hydrocarbons there, and it also helps you with production. Starting with a high pressure is going to allow you to drain those reservoirs when you produce them. Okay, let's go now into horizontal stresses. We're going to see that horizontal stresses actually are quite difficult to estimate. And many of our applications, if not all, are going to be linked to horizontal stress. But let's start first with an example. Let's say that we go offshore again. And at this location offshore, you get a pipe near the seafloor, and you put a balloon here at the end of the pipe. And you start blowing there. What is going to be the shape of the balloon? Well, let's start here on surface. I should bring a balloon, but forgot. If I inflate the balloon, the shape of the balloon is going to be
elliptical.
Say again? In which direction is it going to expand? In all directions, right? Unless it's one of those like clown balloons, like those long ones. But this is not an example, okay? Let's think about a regular balloon. If we blow it, it's going to expand in all directions, and it's going to be more or less spherical. What do you think here, underwater? Is it going to be spherical, or is it going to have a different shape? Well, you're saying smaller because you have higher pressure, right? But let's say we have enough power to make it to inflate it.
Probably smaller on the top.
Same?
Pressure surrounding it is equal.
Small on the top.
Very well.
Small.
It's going to be as long as
Yeah.
the pressure in all directions is the same. The balloon, let me draw here another kind of like three-dimensional view. It's going to be more or less spherical. The pressure is the same in all directions. There is no reason why the shape of the balloon is going to have a preferential distance or a preferential length in some particular direction. It's going to be the same as on the surface, right? Okay, I think we kind of agree with that, okay? what about if now
Because that was the forces. So
we get this wellbore and we make it a casing and we put a balloon now under the seafloor. Now we start inflating again the balloon. What is going to be the shape of the balloon?
It will take the form of the casing around it.
The form of the casing, what do you mean the form of the casing?
You said you drill the casing and then you put the balloon in there and you start inflating, right?
Yeah, at the end of the casing, I put the balloon there.
Inside the casing? No. Or
Outside.
Well, it won't inflate because there's rock around.
But maybe, yeah, close.
he's right.
Let's say that we're strong enough that it doesn't inflate.
Parallel to the least horizontal stress.
Parallel to the least horizontal stress. Okay, I think we're getting closer. Any other idea what the shape is going to be?
It's perpendicular to the least horizontal stress.
Well, in the case it's just fluid, right? There's no rock.
Well, I mean, let's make the example a little bit simpler, okay? So I'm imagining here that this is the casing. The balloon is over there, okay? And all around here, there is, let's say there is sand. I'm wondering what is going to be the shape of the balloon. Not spherical, right? And I think you were saying before also, it's related to, you're saying shape of the void, right?
Yeah, because if it's related to the horizontal stresses, it should fracture it if it becomes such a large force, right? Unless you're not fracturing it, shouldn't it just be the shape of the void?
Yeah.
But you have a membrane here, right? You have this elasticity of the balloon. Well, okay, let's. I hope that you kind of like get the idea that now it's not the same. At least it's not the same as we had before. And what you would have is a shape of the balloon. If we actually manage to inflate this and to make it overcome the forces that are acting on it, it's going to have the shape which is going to be sort of an ellipsoid, and it's going to have the smaller length perpendicular to the direction of something that we're going to call the least principal stress. And in this case, I'm assuming that that stress is going to be horizontal. And because it's going to be horizontal, in this case, I'm going to call this SH mean, which stands for total horizontal stress in horizontal direction. And this is the minimum. If there is a minimum, that's because there is a maximum too, right? And the reason for that is relatively simple. Nature is always lazy. Why would you do work against something if you can get around by not doing it, right? And in this case, it is the same. In this case, the balloon is going to preferentially extend in this direction, in that direction, and not in this one. It's just going to open again that one because that's a minimum principal stress. It's the lowest stress that the balloon is going to face. It's not going to open up in this way, it's not going to open up in that way, because in this case and in that case, it has to overcome a larger stress. Why would you overcome a larger stress if you just can overcome the lowest stress? So all these type of openings, and we'll see later that it's the same with hydraulic fractures, open as a plane perpendicular to the least principal stress. Yes, sir?
So is the balloon opening in such a way that it's compressing the formation around it?
Yes.
Okay, not fracturing, just compressing.
We're going to get into details about fracturing and compression and what happens around, stress around a fracture, usually at the tip of fractures or here at the point of the balloon, you might have tension, and on the face, you will have compression. We're going to get to that later on. But the whole idea here is that now, because we have stresses which are different in different directions, openings in the subsurface are not going to be the same. And because of that, now we can make this concept a little bit more general and say that in the subsurface, we're going to have, now I'm going to do it in 3 dimensions, a total vertical stress, which is what we have been seeing already. There are going to be 2 other stresses, which is going to be the minimum principal stress, which I have chosen the direction in this case to be like that, but it could be in some other direction. And also we're going to have the total horizontal maximum stress. With these 3 values, and knowing the directions of all of those, now we have a full knowledge of the stress state. Notice that, for example, with pressure, you require only to have 1 value as a function of pressure at the given location. With 1 value, you're good. You know what pressure is, that's it. With stress, you need 6 values or 6 unknowns in order to fully characterize stress. You need 3 values for stresses, the actual magnitude of stress, and you need to know also the direction. You need to know, sometimes the vertical direction is the most obvious one. We're going to see later that